everyone. In the previous class, we discussed about the application of Q system to the underground excavation design. We also learned about NATM and NMT. So today we will learn about the modulus of deformation of rock mass and how this can be determined using Q system, using the rock mass number n, and one of the field tests for the determination of modulus of deformation of the rock mass, that is plate loading tests. So first we see that how the modulus of deformation of rock mass can be determined on the basis of various empirical correlations in the non-squeezing ground condition. So various authors have given different expressions for modulus of deformation, and this modulus of deformation is represented as E sub d, or E with a small d in subscript. So the first column gives us the idea about the authors and the year in which they propose these expressions. All these are empirical correlations. So keep this in mind. Then the second one is the expression for the modulus of deformation of rock mass. If there are any conditions for which that these are applicable, that has been given in third column. And if there are any particular cases for which these expressions are recommended, that has been given in the last column. So to start with, first Biniawski in 1978 proposed this expression, that is ED is equal to 2 RMR minus 100, where the condition is applicable that QC should be more than 100 MPa and RMR should be more than 50, and these were recommended for dams. So here this QC is the UCS of the intact rock. Then the next quite popular expression was given by Seraphim and Pereira, that is ED equal to 10 to the power RMR minus 10 upon 40, where this UCS is more than or equal to 100 MPa, and this was also recommended for dams. Similarly, Nicholson and Biniawski in 1990 proposed this expression where they gave the ratio of modulus of deformation to the modulus of elasticity of the rock material. So when I say modulus of elasticity of rock material, essentially we talk in terms of the modulus of elasticity of the intact rock. Then Varman in 1993 came out with this expression for the modulus of deformation, where there is a term called alpha. So what all are the values for alpha? So alpha varies between 0.16 to 0.3, and higher the value of alpha, that means if it approaches towards 0.3, that means it is the poor rock. Then QC is less than or equal to 100 MPa. H, which is the depth of overburden, is greater than or equal to 50 meters. JW's ratings to be taken to be equal to 1. And since these are all empirical correlations, so when they had lot of data, they tried plotting in one space. In that case, the coefficient of correlation worked out to be 0.91. And this expression was recommended to be used in case of tunnels. Similarly, there are other correlations for non-squeezing ground condition, as it is given by Mitri et al. In 1994. It is the expression ED upon ER is 0.5, 1 minus cos of pi into RMR by 100. Then Singh in 1997. This was recommended for dams and slopes, and the second one is for the dams. Here this E sub E is the elastic modulus during unloading cycle from the uniaxial jacking test. Maybe in one or the two subsequent classes we will discuss about this test, uniaxial jacking test. Then Hook et al. In 2002 came up with the expression which made use of geological strength index GSI. Adachi and Yoshida in 2002 gave the expression which used the in situ average Schmidt-Hammer rebound number R, which is there in this expression at this location. Another important empirical correlations, they include the one given by Barton in 2008, where he proposed that the modulus of deformation is equal to 10 times q into qc by 100 to the power 1 by 3, and this should be less than E sub r. The conditions which are to be satisfied include q to be equal to 0.1 to 100 and qc varying between 100 to 200 megapascal, and these are recommended for the tunnels. So this expression should be used in case of the tunnels. For Zhang and Einstein, it is given in 2004. They made the use of RQD and ER to determine the modulus of deformation. Of course, the full range for RQD can be considered, and this was recommended that this expression should be used only for the preliminary analysis and not for the design stage. Then Hook and Diederich in 2006, they came out with the expression which made use of this disturbance factor D and GSI to determine the modulus of deformation of the rock mass. If you recall, in one of our earlier lectures, I have already told you that how we can determine the value of this D. This expression can be used for tunnels, caverns, and also for the dam foundation. So this is how you, using the empirical correlations, you can determine the modulus of deformation. And so you have seen that the use of RMR is there, use of Q is there, use of RQD is there, use of GSI is there. So various empirical correlations proposed by different research workers, and based upon their study, their field study, their lab study, they came out with these expressions. Coming to the average UCS, because this is used in many of the expressions earlier. So this average UCS value for a variety of rocks which is measured on 50 mm diameter samples, they are mentioned here. You are seeing some alphabets in the brackets. For example, you see here I is written, this is M. So this corresponds to I as igneous, M as metamorphic, and S as sedimentary. And wherever you have such type of symbol, for example here, this means that the large variation takes place. So let us say, for example, granite is an igneous type of rock, and typically its average UCS value is going to be about 160 MPa. Say we talk about dolomite. Dolomite is a sedimentary type of rock here, and the average value is although 100 MPa, but the large variation is observed in the value of the average UCS. So similarly, for different types of rocks, you can use this table, and you can pick the typical values. Although we should conduct the tests, UCS tests in the lab to determine the value of UCS, but let us say if we are not able to do, or if we are going for the preliminary analysis and we just need to get some idea, then maybe this table can be referred. Coming to the concept of rock mass number, although this we have discussed earlier as well, if you refer to lecture 35, you will see that we discussed the prediction of ground condition based upon this rock mass number. But to have the continuity, let us come back to this concept once again. So this rock mass number n is complementary to the Q system, and this is defined by this expression where n is equal to RQD by Jn into Jr by J into Jw. Here this factor SRF is not there as it was there in Q system. So basically this SRF value is assigned as 1. So in case of the non-squeezing ground condition, using this rock mass number n, we can predict the support pressure by using this expression, that is PV elastic is 0.12 h to the power 0.1 a to the power 0.1 divided by n to the power 0.33 minus 0.038 megapascal. This is valid for h less than 1400 meter. H means is the overburden depth. In case of the squeezing ground condition, the short term roof support pressure is given as a factor Fn divided by 30 into 10 to the power this expression, which is h to the power 0.6 a to the power 0.1 divided by 50 into n to the power 0.33, and again take a note of the unit megapascal. Now this PV elastic and PV squeezing is the short term roof support pressure in non-squeezing ground condition and squeezing ground condition respectively, and both are in megapascal. Fn is a correction factor for the tunnel closure, and H and A, they are tunnel depth and tunnel radius in meters respectively. Remember, this is tunnel radius, A is tunnel radius and not the diameter. Now, how to determine this correction factor is given in this particular table. So, it depends upon the degree of squeezing, and accordingly we can define, or we will have the normalized tunnel closure. This also we discussed in some of the earlier classes, that how on the basis of the normalized tunnel closure and that plot, if you remember, I showed you how on the basis of that some demarcation lines were made which were identifying various zones of very mild squeezing, mild to moderate, moderate, high and very high squeezing. So here corresponding to the degree of squeezing, you will have the normalized tunnel closure in the percentage. So how this is defined, it is UA upon A in percentage. So based upon that, you have the correction factor given in this table. For example, if the rock mass is experiencing or going through the moderate kind of squeezing, having the tunnel closure between 4 to 5% of the radius of the tunnel, then in that case this correction factor to be used should be 0.8. In the non-squeezing ground condition, the tunnel closure can be determined by these expression, that is UA upon A is equal to h to the power 0.6 divided by 28 n to the power 0.4 into k to the power 0.35, and this is in percentage. Similarly, for the squeezing ground condition, one has to use this expression to determine the tunnel closure, which is the normalized tunnel closure here. So this is a normalized tunnel closure in percentage. K is the effective support stiffness, which is written as PV into A upon UA. Here this is Ka is also in megapascal, and H and A, they are tunnel depth and tunnel radius in meter respectively. Now you see here, there is a limit to the allowable UA upon A. It should be within 4%. If I have that permissible limit of UA upon A with me, and say if it is the non-squeezing ground condition, then I can focus on this particular expression. I know this quantity because it is the permissible one. I know H, I know N. So using this expression, I can find out that what will be the required stiffness of the support system, so that the closure or the normalized closure is limited to that much of the percentage which I am giving as input here. So this expression, although if we know the support system stiffness, we can find out what will be the tunnel closure, but it is used other way around in a better manner, that if we have the permissible value of UA upon A, then we can find out that what will be the required effective support stiffness. Now, before I go for the field tests for the determination of modulus of deformation, once again let us discuss about the difference between modulus of deformation and modulus of elasticity of rock mass. In some of the earlier lectures we have already discussed this, but let us do this again. The modulus of deformation of the rock mass is defined as the ratio of stress to corresponding strain during loading of a rock mass, including elastic and inelastic behavior. Now, let us say that I conduct a test where I load it and then unload it and further load it, and likewise I have few cycles, as it has been shown as a typical stress versus deformation curve in the deformability test of the rock mass. So, the first cycle loading, then unloading, then second cycle loading, unloading, third cycle, fourth cycle, and then fifth cycle, and similarly you have the unloading part as well. So, you see, to find out the modulus of deformation, we have to consider the total deformation, that means including the linear as well as the non-linear portion. But in case of the modulus of elasticity of the rock mass, we have to use the ratio of stress to the corresponding strain during loading of a rock mass, including only the elastic behavior. So, how we can do that? Which deformation should we take? When we unload it, the elastic part of the deformation is recovered and the plastic portion remains as it is. So, you see that corresponding to the last cycle, this has been shown. After this loading, the system was unloaded, and here this much is the deformation which is recovered, which is WE. So, this is being used for the determination of modulus of elasticity of the rock mass. However, this complete WD will be used for the determination of modulus of deformation of rock mass. So, that is what is the basic difference between the two. Now, let us take the first in situ test for the determination of modulus of deformation. This is called as plate load test. So, here what we do is, in the rock mass, we prepare an edit, and there we apply or we put the plates on both the ends, and then we apply the load onto these plates, and then we measure the deformations. So, this is how we carry out the plate load test. So, this is the measurement of the displacement at the loading surface of the rock. So, it is not inside the rock mass, but at the surface of the rock mass. Then the measurements can also be performed in walls. So, here an example is given for the roof. But then if you conduct the tests in the horizontal position, then you can take the measurements in the walls as well. Let us take a look at the test setup, and this will make things clear to you. We use the rock surface in a drift. So, you see that this is the drift that is prepared. So, the rock surface in the bottom and top of the drift, that means here this is what it is, the rock surface. This is smoothened by chiseling to get the more or less parallel faces about 5 centimeter or more than the diameter of the test plate. So, if the test plate has, let us say, the diameter of 60 centimeter, accordingly the smoothened surface or a smoothened parallel face will have the dimension about 5 centimeter more than that. Then we need to provide the reaction pads which take the reaction for the loading. So, you see here how the plates are placed, and in between the plate and the rock mass there is a reaction pad. So it not only ensures that both are in contact with each other, but then also takes the reaction for the loading, because if it is not in contact with each other, how will you get the deformation characteristic of the rock mass surface? So the test plate size of 60 centimeter diameter is used. So you can see here that 60 centimeter dia plate is there, which is in contact with the reaction pad, and on top of that we put another plate which is 45 centimeter diameter, and then somewhere in between we have the spacers, and with the help of this hydraulic pump here that is shown, we apply the load that is being mobilized, and it tries to push the plates in this direction. So once the loading is applied, there is going to be the deformation at the surface. That displacement is measured by the extensometers, and the load that is applied is through the hydraulic jack, which is shown here. These extensometers, in case if you have to measure the rock mass deformation, then we go for the use of extensometer. When we discuss the chapter on instrumentation and monitoring, we will discuss in detail different types of extensometer, their working, etc. So what we do is that we apply the load, then we wait for some time the deformation to take place, then we remove that load in the stages. It is exactly the same as you conduct cyclic plate load test in case of the soils. So you see various points, they tell you that okay, this was the load increment and the corresponding deformation, and while unloading also it is done in steps, not that immediately whole of the load was removed. So first cycle unloading, then again it is being loaded, unloaded, and the similar thing is done. So from here we can obtain what is the deformation corresponding to any load. For example, let us say corresponding to a particular load, if you divide that by the area of the plate, you will get the stress in megapascal. So let us say corresponding to 5 MPa, what is going to be the total deformation? So we just drop it here and maybe approximately 0.25 centimeter. But then what is going to be the elastic displacement here? So upon unloading, this much has been recovered. So this is what is going to be WE in case of the last cycle. So how can we determine the modulus of deformation or the elasticity? See, both we are doing, and I just explained you that what is the difference between these two. So based upon that, here W value will be either taken as WD or WE. Accordingly, you can determine either the modulus of deformation or the modulus of elasticity. So the units are kg per square centimeter. P be the applied load in kg, nu is the Poisson's ratio, m be the constant depending on the shape of the plate, and this is going to be equal to 0.95 for square plate and 0.96 for the circular plate. And W be the deformation corresponding to the applied load, which is P, and A be the area of the plate. So we use this expression, that is E equal to P into M 1 minus nu square by W into square root of A to determine modulus of deformation or modulus of elasticity, where all the other variables are mentioned here like this. So this was all about the plate load test. The two references apart from the one that I gave you in the beginning of this course are mentioned here. So this material is taken from these research papers. Maybe if you want to look into more details, maybe you can refer back to that. So what we discussed today is about the modulus of deformation, how it can be determined from the empirical correlations, how it can be determined using RQD, using RMR, using Q system, using GSI. Then we also discussed some aspects related to rock mass number n, followed by our discussion on the in situ determination of the modulus of deformation. And in this connection, we discussed the plate load tests. So, in the next class, we will discuss few other in situ tests for the determination of modulus of deformation. Thank you very much.